Well, we're going to have a short discussion here about round things, and we've talked about this picture here before, and this was the real life scenario, this is the idealized model, and then the free body diagram. A couple of things I just want to mention about round things. We're only going to consider uniformly distributed weight round things, and what that means is the center of gravity of a round thing is in the center. That may be obvious, but that's the way we're going to consider all round things for now. The center of gravity is from the center, and that acts downward from wherever it's at. Second thing about round things is there's usually something holding it up, and that normal force will be perpendicular to the contact surface, perpendicular to the contact surface, perpendicular to the contact surface, right there. And because the contact surface, because it's round, that contact force goes through the center of gravity. So all the line of action of the contact force is going to go through the center of gravity on this side. The same thing over here. There's a contact surface here, and it's going to go through that point, also through the center of gravity. So if you look carefully at the free body diagram, the contact forces go through the center of gravity. The weight will be emanating from the center of gravity and always going down. Second thing is what happens on inclined planes, and this is something we just talked about in the prior video, but whatever the angle that the inclined plane makes with the horizontal is the same that the normal makes with vertical. So in this case, vertical will be the weight, and the normal force, the contact force, will have that same included angle. So if this is angle 30 here, this is going to be the 30. Okay, so I've just written it down here. The slope is the angle that the surface makes with horizontal. This is the same angle that normal makes with vertical. So how do we draw free body diagrams then? First of all, if we draw the free body diagram of this one, I've just drawn it. Actually, let's draw the free body diagram of this one right here. So I've drawn, this is the top one right here. It's got a weight, it's got an mg sine theta, an mg cosine theta, it's got a normal force. What keeps it from rolling down the hill is this force from C, or this force right there. I've called it C, but it's right there. Something keeps it there. This mating force also, because there's a contact surface here, that mating force has to go also through the center of gravity. If I were to draw the free body diagram of the one below, it's going to have a similar configuration. It's going to have a weight, an mg sine theta, an mg cosine theta, a contact force here at D. It's got a normal force, but it also has this force here, equal opposite. In other words, if it's pushing up on this one, it has to be pushing back. If it pushes up on this one, it has to be pushing back on this one. So if I separate the free body diagrams, that contact force has to be equal opposite as it touches those two discs, or those two pipes. If I solve it all in one spot, then I consider this an internal force and I don't have to worry about it. But for now, if I draw separate free body diagrams, I must have that contact force. If I draw them together, then that's an internal force, and that D will still be the same. Okay, how about something like this? This is just a little more difficult, if you will, but this is a question about how much force does it take, or how much force is required to push this one up the hill. So let's just draw the contact forces and the forces. I'm not going to draw a complete free body diagram. I just want to make sure that you're aware of how the forces are drawn. But let's say that this one has a weight. It has a contact force at B. It also has a contact force at A. And there are components, and we can draw the positive and negative, or the sines and cosines of all these things. Let's go over here to C, or let's go to the second one. There's a contact force here, there's a weight, and this one's being pushed, so there's a force there. But there's also a force in between them. And that force in between them, if I go back up to here, and I'm going to say that this is going to be the angle of the contact forces. So if I draw that contact force here, it's going to be from this point. This will be the line of action, and it'll be going like that. And this one will have the same force the same line of action. And I'll call that, do I have a letter here? I'll call this F. And that's the contact force between the two. It has to go equal opposite on those things and along that line of action. Anyway, that will help you get started on some of these round things and inclined plane problems. It'll be, they're not very easy. Sometimes the trigonometry gets pretty tricky. Well, here's one that is fairly straightforward. And what we have here is a wagon. It's got a load of sand in it, and it's got some dimensions. It says the weight in the wagon is 1,000 pounds or 1,000 newtons. And my question is, will it jump the wall? And what do I mean by jumping the wall? I got a 200 Newton force here, 200 Newton force. Would you agree that if it jumps the wall, it basically moves up just a little bit? It's going to move up a little bit. And then as soon as the wheel gets on top here, then it'll start moving forward. And that's kind of what I'm referring to when I say jumping the wall. I want to find out if I have enough force to get it up and going. Well, I've got a lot of forces on here, so for convenience I'm not going to draw a separate free body diagram. I'm just going to draw the forces on this picture. Unfortunately, when I ask you guys to do problems on homework and exams, I will want you to draw a separate free body diagram most of the time. But in this case, I'm going to draw this 1,000 newtons coming down. There's going to be a contact force here, and I'll call this A. I don't have a letter on there. There's also a contact force right here. I'll call this B. And where the wall sticks up here, right here, there's also a contact force right there. And it is going to be perpendicular to the contact surface, pointing through the center of the wheel. So I'm going to say that this is going to be C, right like that. The line of action, actually I didn't do that very good. Let me do this again. I'll say that the force goes that way, and then the line of action goes right through the center. Same here, saying line of action goes through the center of the wheels. Alright, do I have enough force to jump the wall? Alright, is this a stability question or an equilibrium question? Well, it's really an equilibrium, it's really a stability question. Do I have enough force for it to become unstable? And so if it is a stability question, what is something that we usually ask when we're talking about stability questions? In other words, does it have a force for something to jump the wall, or is it for it to move? Something usually happens under a stability thing. So can you guess what happens if this becomes unstable? Well, what happens is B goes to 0. In other words, it becomes, the force there goes to 0, and so then it has the ability to move, if you will. So at tip, and I'll call it at movement, I'll say that B goes to 0. So what my approach here is going to be is I want to solve this as a equilibrium problem and find out if there is a contact force at B, and if there is a contact force at B, then it is in a stable configuration, and it really is an equilibrium, and it's not an unstable situation. So it's kind of a long, drawn-out explanation for how to get started on this. But let's go ahead and find the reactions at A and B, and let's see if B actually has a reaction. All right, so that's going to be our problem approach. I'm going to zoom out just a little bit so I can get a little more on here, and let's start summing some moments. I'm going to sum the moments about point A. Okay, so I've written out the terms here just to save a little time. I got this 200 times this lever arm. I'm going to sum the moments about at that point right there. Some of the moments about A. 200 times this lever arm, 1,000 times this lever arm, both going in the negative direction. And this is half of 750, so that'd be 375. B is going in this direction. It's got a lever arm of 750. Then I got C here. This is the contact surface, or the contact force. Its lever arm is half the diameter of the wheel, so that would be 0.125. Then I have this pulling up force of 200, and its lever arm is 0.75 plus 0.375, and that's equal to 0. Now, how many unknowns do I have? I have B and C, so I can't really solve that yet. So let's see if we can find out one other equation to solve for one of those forces, and then find out if B has a value or not. So I'm going to sum the forces in the X. And in that case, you can see that there's only one other force in the X. We got that one and C right there. So I'll go ahead and do that. So I summed the forces in the X direction, and I found that C is equal to 200. Plug that back into here, and I can solve for B is equal to 300 newtons. Alright, so is this moving or not? Is this a stability or an equilibrium problem? Right now it is still in equilibrium because there is a normal force at B. That means it is not moving, and therefore it is stable in its current configuration because B is a positive number and not moving. I do it as a positive number. I've solved it as a positive number because it's positive and not moving. It is stable the way it's at. Well, the next short concept is, what if the wall is small like this? What does it take for it to roll over the wall or jump over the wall when it's smaller like that? Well, let's go ahead and draw the forces in, and we'll see what they might look like. We have an mg. There's probably a normal force. And there's a contact force here, and we know enough now to say that that contact force has a line of action that goes through the center, and there's going to be a height h of the block. We also know that this is the radius r. What we can do is draw this little internal triangle here, and we can define this as angle theta, and this is going to be the same angle theta, right like that. Whatever this contact force is, we'll call this C. This will be C cos theta, and this one will be C sine theta. And the lever arms are going to be defined by this little triangle right here. So if you say that this is theta right there, this is going to be r cos theta, and this is r sine theta. This total distance here is r. This is distance h. So I'm just going to write some identities here. R minus h is equal to r cos theta, or h is equal to r minus r cos theta, and that's kind of handy to know. Either one of those can be used to find the angle theta when we're doing that. And then of course this lever arm here is r sine theta. So when we're solving some equilibrium problems, it's just helpful to know that this is the lever arm for the cos theta contact surface, and this often, because this is going this way, this will be the lever arm for the for this other force as we're trying to solve it. And what we've got here is a homework problem I want you to try to work on. And I'll give this to you with dimensions and weights, but we're looking for what force P is going to take for this problem to jump the wall. And oops, let me push that back up again. What force P does it take for this to come up and jump over the wall? It's got a little dimension there. Alright, good luck with that homework.